So welcome everyone to today's algebraic graph theory seminar. Today we have Krystal Guo speaking from the University of Amsterdam, and she'll be talking about simple eigenvalues of graphs.
Okay, hi everyone. I'm unmuted now. Fine. All right, Max is nodding. That sounds good. All right, so today I wanted to talk about simple eigenvalues of graphs. And this seminar, when it was run, live and stuff, it used to be more of a learning seminar where we would learn about old results instead of presenting new ones. So in sort of, in that spirit, I'm going to spend some time going over some properties of simple eigenvalues of graphs, as well as, some newer results. So yeah, let's get started. So what do I mean by simple eigenvalues? So if I have a graph G, sorry, Chris, I know you like it to be X, and A is its adjacency matrix. So we look at the eigenvalue lambda, and it just means that AV is lambda V for some V, which is a vector that is not 0. And an eigenvalue is simple if it has multiplicity 1. Okay, so here in algebraic graph theory land, we speak of eigenvalues of the graph and of its adjacency matrix interchangeably. And we'll always be using adjacency matrix for this talk. And when I say that G has simple eigenvalues, I mean that every eigenvalue has multiplicity 1. So there is some ambiguity because I will want to speak about some graphs which have some eigenvalues that are simple, but I also will want to talk about graphs where every eigenvalue is simple. And the phrase, the graph has simple eigenvalues is a bit ambiguous, but here I want it to be that every eigenvalue is simple. Okay, so let's continue. So when do simple eigenvalues occur? So the Perron-Frobenius theorem says that for any matrix with non-negative entries, the biggest eigenvalue is always every matrix with some stipulations. It gives you that if the graph is connected and non-bipartite, the biggest eigenvalue is always simple. So, oh, okay, that's not good. Lambda 1 is always simple. And Chris, I do admit this Y is dubious when the G is connected. And if G is bipartite, the matrix will have this bipartite format. So if you apply one of the other cases of the Perron-Frobenius theorem, you get that lambda 1 and lambda n, the smallest eigenvalue, are both simple. If G is bipartite and connected. Okay. So thus, every connected graph has at least one simple eigenvalue. Okay, what about graphs with all simple eigenvalues? So what I was saying, graphs with simple eigenvalues. So an example of such a graph is the path. So the path graph, every eigenvalue is distinct. So they are 2 times cos of pi k over n plus 1, Pn, the path on n vertices, and k goes from 1 to n. So the way that you see this is you can embed the path in a cycle of length 2n plus 2. So the path of Pn, and there's 2 copies of Pn here, Pn, and then 2 vertices here. And then you can construct eigenvectors for this larger cycle where these entries are 0. So that you would get an eigenvector for Pn, which is why all of the eigenvalues are the real parts of the 2 plus 1th roots of unity. No, 2 plus 2 roots of unity. And then how do they look? Well, okay, in the complex plane here, the roots of unity are on the unit circle. 1 is here. So we're taking the first n of them, and there are 2n plus 2. So all the roots that we're taking are somewhere like this. And if we take their real parts, we're just taking their images when you project down to the real line. So clearly they're going to be distinct. I'm not going to take some root that is down here. Right? So this will always give us a graph with distinct eigenvalues. So is the path so very special in that it has all simple eigenvalues? Well, the answer is no. There is a recent-ish theorem. I mean, it's before 2020, and 2020 has been very, very long. So maybe it's not that recent. So there's a theorem of Tao and Vu that says that as n goes to infinity, the proportion of graphs on n vertices which have simple eigenvalues goes to 1. So in other words, almost every graph has simple eigenvalues. And if you do some computations on little graphs on up to 8 vertices, you can see for yourself that even when n is very far from infinity, this is also true. Very large proportion of the graphs do have simple eigenvalues. Okay, so what are some of the effects of the graph having simple eigenvalues? Well, there is this graph isomorphism thing where if I have two graphs, I want to determine if the two graphs are isomorphic. And the complexity of this problem is very much in dispute. And progress has been made in recent years. But in '82, Leighton and Miller had a graph isomorphism algorithm that was in polynomial time if both inputs are graphs which have simple eigenvalues. This result was never published because it was immediately subsumed by the paper of Babai, Grigoriev, and I can't read my handwriting, in '82, which proves the same statement, but for graphs with eigenvalues of bounded multiplicity. So, right, but this original algorithm was never published. So how does this algorithm work? So naively, what you can think of is I have two graphs and I want to know if they're isomorphic. So the first thing I can do is I can find their eigenvalues and see if these things are equal. Because if they're isomorphic, then the eigenvalues have to be equal. So if I find that the eigenvalues are not the same, or I compute the characteristic polynomial and I don't get the same polynomial, then I know the graphs are not isomorphic. So we do that. And the graphs have simple eigenvalues. So if you consider if one of the graphs is just an isomorphism of the other graph, so it's just the same graph, but with everything permuted. So all these eigenvectors, because they are dimension 1, we can normalize them. So we can assume that the vertices are 1 through n, and then we look at the eigenvector corresponding to the biggest eigenvalue, lambda 2, corresponding to the second biggest, lambda n, lambda 2, sorry, and so on. And these are all distinct eigenvalues, so that's why there's a greater sign. So if I look at their eigenvectors, I can normalize the eigenvectors, so they all have norm 1. So if the two graphs are in fact isomorphic, if I do this for the other graph, which I didn't bother to write out, then these vectors should be those other vectors just permuted, right? So then a naive algorithm would be to look at the entry of each vertex in this lambda 1. By the Perrin-Frobenius theorem, again, we know that these entries are positive. Let's assume the graph is also connected, okay? So I can just look at how big these entries are and decide how to send these vertices to the vertices of the other graph, right? What's the problem with that? Well, the only problem is that you could have a tie. You could have like two entries that are the same in this eigenvector. That's not illegal. So what would you do then? How would you map these two vertices to whatever two other vertices, I and j, sorry, which also have a and a in lambda 1 eigenvector? Well, okay, you have all these other eigenvectors. They're basically going to be the same up to sign and permutation, and you're determining the permutation. So you can just look at the whole row, this list of entries, and then you can ask, okay, when you can sort of try to use these to determine which ones to send, suppose this was vertex 3, whether I send 2 to I or 3 to j. So will this work? Well, how would it work? It would work if I take the absolute values. If I take the absolute values of all of these, this is v2 of 2. If I take all of these absolute values, vn of 2, and I form a tuple, this will be a legitimate algorithm if this tuple would be the same only when those two vertices are in the same orbit. So is that true for a graph? Not a rhetorical question. You're allowed to answer. Oh, I see Chris pushing a unmute button. What do we think?
You want to? No.
Okay, right, they're not, because you can take strongly cospectral vertices, and this would always be true. Or just cospectral in this case. So anyway, you can construct vertices that are not in the same orbit. There's no automorphism that takes one to the other, but yet when I construct this vector that consists of all the absolute values, they're going to be the same. So this is a problem that sort of compounds. That you always have these pseudo orbits of vertices, and you cannot decide how you send them to the pseudo orbits of vertices on the other side, and then you just have a smaller graph isomorphism problem to solve. So this naive thing, it seems like it should work because the graph has simple eigenvalues, has very simple structure in terms of the eigenspaces. And yet it doesn't. It almost feels like we need like more machinery. And what is the more machinery that we need? Well, the more machinery that we need is star canonical bases. What you need to do is you need to associate vertices to eigenspaces of the graph. So in general, here is what would need to be done. So in general, you form the bipartite graph as follows. You have, so not for simple eigenvalues, for general arbitrary graphs. Let's say you have k distinct eigenvalues. I'm sorry, I need m for something else. So I have the k distinct eigenvalues of the graph, and their multiplicities are m1 through mk respectively. Okay, so then I want to form the bipartite graph as follows. So on the left side of the graph, I have the vertices of the graph, v1 up to vn, say. And on the right-hand side, I have mi vertices corresponding to each eigenspace ei, where mi is the, so these are sort of like the eigenvectors of the graph, but they're not explicitly, I don't tell you which eigenvector it is. They're just 3 vertices associated with an eigenspace of dimension 3. So this is the right side of the graph. So what's going to happen is for every possible partition, for every possible perfect matching between these things, I assign some weight to it. So I add all possible edges. So I will have a complete matching between them. And what I would, so this will be k and n in the end. And what I really want is I want to choose one perfect matching. So we want to choose one perfect matching of this business here, such that if I look at the vertices that are xi are the vertices matched to ei, the ith eigenspace. So I'm matching some vertices to some eigenspaces. And I want the property that if I take, ei times, so the first thing is an I times the elementary basis vector of j for each j in the things that I assign to the eigenspace. This set of eigenvectors spans the lambda j eigenspaces. So somehow I want a specific basis of all the eigenspaces such that they consist of these ei, ej's, or this is the elementary basis. And such a basis is a star basis. Okay. Or equivalently, I want to partition the vertices of the graph into xi's corresponding to the size of the eigenspaces, such that when I delete the vertices of xi from G, the resulting graph does not have lambda j as an eigenvalue. Okay. So I think this is called something else. This is called the polynomial partition of the graph. Partition of the graph. And the partition into xi's given as this is called the star partition of the graph. And it just happens that these two concepts coincide. But in any case, what I really want to find is a partition of the vertices of the graph into the same sizes as the eigenspaces, and then match those parts to the eigenspaces appropriately, such that the eigenvectors induced by this form a full basis. Okay, so if I manage to do this, in the end, I will have some association between vertices and eigenspaces. What will happen is for each group of vertices, each xi, there will be a set of eigenvectors or an eigenspace or an idempotent projector onto that eigenspace, which is special to it. And this is what we will be able to use to solve the graph isomorphism problem, even for arbitrary graphs. So for arbitrary graphs, the issue is that finding these things is maybe not easy, but what you would really like to find is not just find any star partition, but you wish to find a canonical one. So for example, if you would line up all the star partitions and take the one lexicographically first, if you would take the inner products of all these vectors, that will be a canonical choice. So if you had two graphs and you could compute the canonical star partition for both of them, then you will be able to determine graph isomorphism. And the issue is that if the eigenspaces would have huge multiplicity, then you can't do this efficiently. But in the very special case that your graph has simple eigenvalues, the picture is a lot simpler. So all you have is the vertices of the graph on the one side. And on the other side, you have the eigenvectors, okay? And then what we're gonna do is we're gonna put a matching edge, an edge between the vertex and the eigenvector if that vertex is in the eigenvector support. So VI, so if V1 is not 0 on vertex 1, then I put the edge and I add a weight of the absolute value squared of that entry, right? So if you put the edges arbitrarily with the same weight, you would get weight 0 for the edges that I don't allow you to put. So yeah, so on this edge between vertex 2 and eigenvector n, I put the value for 2 in this eigenvector squared. So in the end, I will get a weighted bipartite graph. So this will give me a weighted bipartite graph, okay? And then the thing is, all I have to do is find a maximum weight matching. Okay. And such a matching, this will be a graph invariant. If I do this for an isomorphism of the graph and I find the matching, it will still be, it will be invariant because it's the matching with the biggest weight. And these weights are not, this entry of the vector, it's not, its absolute value is not changed by the isomorphism. So what I will get is I want the maximum matching. So I want the pi such that pi of I is the edge that is mapped to, that is matched to VI. Okay, so what this will give me is a permutation of the vertices, in fact, into this matching. So I'm going to get this pi. Okay, so the pi, it's just however you chose a perfect matching, and then you will be able to assign the indices of the vertices over here to the vertices over here. So then what I will do is reorder the vertices as pi 1, pi of 2, pi of 3, so on, pi n. So if I do that, there's a theorem of Tvekovich, Rollinson, and Simic that after you do this to both graphs, so if you have G1 and G2, and they both have simple eigenvalues and the same simple eigenvalues, if you do this operation to both of them, you reorder both of these graphs in this order, then they're isomorphic if and only if the adjacency matrices are equal. Right, so part of this is not surprising. So if the adjacency matrix were equal, then the graphs have to be isomorphic, obviously, but you can have isomorphic graphs and their adjacency matrices aren't equal because you're allowed to apply this permutation. But once you do this ordering of the vertices, it is a canonical choice. They have to be, the adjacency matrices have to be equal if the graphs are isomorphic. And again, when you try to prove this theorem, you do have to deal with what happens with vertices that are in the same orbit, and it does work out in this case, because what you get is that you have the spectral decomposition of the graph. So you know that A of GI, maybe this page slides, okay, A of GI, it's a sum over some lambdas of these VIs, right? Lambda I VI, sorry, VI transpose. Yeah, that results in a square matrix. Okay, not a 1-by-1 matrix. So you have the spectral decomposition, and once you reorder, because your your two graphs, these vectors are basically the same in absolute value, except in absolute value, and you have the same lambdas, then you really get that it's equal to the adjacency matrix. So you don't have the same problem as before. Okay, so any questions up to this point? So the reason I wanted to talk about this is the reason I wanted to talk about this is because, I mean, there's some confusion, right? The naive algorithm of you just assign it with a tuple of all the entries in the eigenvector, that it should work. It's very attractive because it's very easy. And you think that if it works with simple eigenvalues, this is how it should be. But it's a little bit weird that you have to go through all this machinery with a star canonical basis. And this is not easy to establish. And you can imagine that for graphs with larger multiplicities, you would have to solve the same problem, but you would need to find some sort of cliques, which is fine if the size of the cliques are bounded, which is why, which confirms the result of Babai et al. That graphs with multiplicity or eigenvalues of bounded multiplicity, you can solve graph isomorphism in polynomial time. Okay, but what is interesting is about this algorithm is it really asks for vertices to have a relation to the eigenvectors, that you really want to associate eigenvectors to vertices of the graph. And we see this in other areas of graph theory. Like we were just talking about this paper, which claimed to disprove the existence of the Moore graph. So for strongly regular graphs, you can talk about formal duals and even formal self-duals of the graph, wherein there could be a mapping from the eigenvectors of the graph to the vertices of the graph, because the multiplicities of the eigenvalues work out. And that's a related idea to these star bases, star partitions, and canonical star. I don't know, there's a lot of words. There's canonical and star and ordering. But yes, so it's sort of like an important idea. And I wanted to sort of bring that to the world of simple eigenvalues before I prove more things about simple eigenvalues. Okay, so everyone's good for the algorithm? Okay, excellent. So for vertex-transitive graphs, let's move on to the results that I actually wanted to talk about. So if you have a vertex-transitive graph, there is an automorphism which maps any vertex x to any other vertex y. Okay, so suppose you have a vertex-transitive graph and it has some simple eigenvalue lambda. Okay, and then you have your eigenvector v such that AV is lambda v. So if we look at any element of the automorphism group, P, we can represent it as a permutation matrix, which satisfies that if you conjugate A by P, keeping in mind that P transpose is equal to P inverse, you just get A. So then keeping that in mind, A times P of V, this is just, I can replace A by this business here. So P A P transpose times PV, but we recall that P transpose is just P inverse. So I just get P A V and I get lambda PV. So at the end of the day, what happens, P times V, if I permute the eigenvector corresponding to the automorphism of the graph, then it's also an eigenvector for the eigenvalue lambda. Okay, but lambda is a simple eigenvalue. So it only has one linearly independent eigenvector. So this P times V, this permutation has got to be a permutation of it. Sorry, it's got to be a multiple of the original eigenvector. But we didn't do anything special. We just permuted the entry. So we didn't change the norm of the vector. So PV has the same norm as V. So then the only thing that could have happened to it is you could have flipped the sign. So this PV, it's either V itself or it's negative V. Okay. But the graph is vertex transitive. So that means that I can map any vertex to any other vertex using this permutation. So what that basically means is that every entry of V has the same absolute value. So because the graph is vertex transitive, all entries, okay, perhaps we write this way, go back. V of X is equal to v of y, all vertices x and y. Okay, so the only thing is that they're plus or minus. So we may as well normalize such that this v is a plus or minus 1 vector. So basically v is plus or minus 1 to the n, where n is the number of vertices. Okay. Okay, so what does it mean for a vector v to be an eigenvector of a graph? Well, it means this equation here. Okay, but let's unpack that. In particular, if I look at a vertex x, I can look at the row of this whole equation corresponding to vertex x. So what would I get? On this side, I would just get lambda times whatever value v takes at vertex x. And on the other side, I get a times v, which is a sum of all the vertices adjacent to x of their values. So what does it look like if I look at it in the graph? I know that I already scaled my vector v so that all the entries are plus or minus 1. So I know this is like maybe a -1, this is a 1, -1, 1, -1, something like this. And x, its value is either plus or minus 1. So what do we get? Well, let alpha be the number of -1s around x. Okay, so then lambda times this plus or minus 1, it's just equal to the degree of the vertex, which let's say is k, because it's vertex transitive, so it will be k regular. Okay, so it's going to be k, and then minus 2 alpha, because alpha is a number of -1s. Right. So what does this mean? This means that lambda is a plus or minus k minus 2 alpha. Okay. So at the end of the day, what we've obtained is that we can write a simple eigenvalue as k minus 2 alpha, where alpha is an integer. So if you have a simple eigenvalue of vertex transitive graph, this is what it has to be. It has to be an integer, and it has to be the degree minus an even number. Okay. So if G is vertex transitive and all the eigenvalues are simple, then, well, the eigenvalues are some k minus 2 alpha, but what can alpha be? The biggest eigenvalue of an R regular graph is k, and the smallest eigenvalue that it could be, if it were bipartite, is minus k. So this alpha, it needs to live between 0 and k. Okay, so there are n eigenvalues because there are n vertices. And what does that mean? So how many distinct ones of these things can there exist? Well, there are only k plus 1 of them. There are only k plus 1 distinct eigenvalues here. So k plus 1 is equal to n. Okay. So, but k is also the degree of the graph. So basically you have to have kn. But we know that the eigenvalues of kn are n minus, well, that was distressing. N minus 1 with multiplicity 1, and minus 1 with multiplicity n minus 1. So these are not going to be all distinct unless G is K2 or K1. Awesome, right? So if you have a vertex transitive graph where every eigenvalue has multiplicity 1, then your graph is the complete graph on 1 or 2 vertices. So intuitively, what we want to say is that many automorphisms sort of corresponds with few simple eigenvalues. Okay, sure. Right, so this is intuition. It's pretty much, it's okay, right? Okay, so let's move on to a very specific case of some work I did with Boyan. When we did this when I did my PhD, and we took a while to paperize it. Sorry. So if we consider cubic vertex transitive graphs, so vertex transitive graphs where every vertex has degree 3, what are the possible simple eigenvalues? It should be 3 minus even number, right? So it can only be 3, 1, minus 1, and minus 3. Those are the only possible choices. And you know that if 3 and minus 3 are both eigenvalues of a cubic graph, then it has to be bipartite. So what we showed is that if 1 and -1 are both simple eigenvalues of a cubic vertex-transitive graph, then it also has to be bipartite. So it's not possible for the bipartite, sorry, it's not possible for cubic vertex-transitive graph to only have 3, 1, and -1 as simple eigenvalues. Like you would also need to have -3. Sorry, and the graphs are also connected, so we don't have to worry about multiple components of the same graph. Okay, so then the idea that I had when I was a young PhD student is that the cubic vertex transitive graphs, they have very many automorphisms. They're vertex transitive. So if I require also that they have many simple eigenvalues, like as many as it could have, which in this case is like 2. 2 is also very, very many already for these graphs since they have possible maximum 4. Then there should be very few graphs. And then perhaps we could classify them. So the answer to this question is no. But we can prove some properties about them. So what we did was we proved some properties of such graphs, and we found many infinite families where we could characterize when these would occur. And then if you look at the senses of cubic vertex transitive graphs, so some people, Pablo Spiga and Gabriel Verret, have kindly compiled for us all vertex transitive cubic graphs up to about 1,000 vertices. So you can just search the senses and see. What I was hoping is that there would not be so many sporadic examples that didn't live in any of our constructions, but in fact there are. So that's slightly sad. But nevertheless, we do have some really cool examples, and showing that they have simple eigenvalues turned out to be really interesting. So perhaps let me show you a bit more. Oh yeah, so by the way, that bipartite thing, it could be sort of extended. If you have 2 simple eigenvalues of a k-regular graph, if they're both simple eigenvectors, simple eigenvalues, okay, and they come with eigenvectors v and w, then the Hadamard product or entry-wise product of those vectors is also an eigenvector of the graph. And the eigenvalue is this thing here. And no, it is not a typo. This is supposed to be an A, and this is the alpha from here. So there is just some A that is not really possible to know without knowing what the graphs are, but it gives this thing. So if you have k minus 2 and like minus k plus 2, as eigenvalues, what happens is, depending on what the value of A is, either you get that minus K is also an eigenvalue, in which case the graph will be bipartite, or you get, I think, minus K plus 4 as an eigenvalue. And it depends on what A you get out of this formulation here. So you cannot really exactly extract anything because I cannot say anything about what the A is without knowing more information about the graph. But some other stuff related to that previous bipartite theorem is possible. Yeah, so perhaps if you said that your graph had many of these integer simple eigenvalues, then using this thing and somehow proving things about which A's has to occur, you could force the graph to be bipartite. This is possible, but I'm not very sure. Okay, so one family that we looked at that could be vertex transitive and also could have 1 as a simple eigenvalue is the generalized Peterson graphs. So the generalized Peterson graphs of nk, so it comes with 2 parameters, n and k. So n is the number of vertices in the outside ring. So what happens is you have n vertices on the outside, which you connect always as a cycle. So you always connect every vertex to its neighbors. And then in the inside cycle, you also have n vertices, and you connect them with a skip based on k. So here k is 1, so I do connect to all the neighbors. And I connect the outside and inside cycles with a perfect matching. So this graph is the Peterson graph. It's also a generalized Peterson graph, as you would expect. N is 5 because each of these cycles is 5. There's a perfect matching between them. And for the inside cycle, I connect things that are 2 apart. So this is 2, 2, 2, 2, and I would get a 2. So this will give me a cubic graph, unless what happened in the middle is I got a perfect matching for some reason. So if the parity of n and k would be the same, then I would somehow get a matching or something in here, and even. So I wouldn't get a cubic graph. But if I would get a cycle in the inside, I would get a cubic graph. And you can show that this graph P and K is vertex transitive when nk are 10 and 2, or when k squared is plus or minus 1 mod n. So the Peterson graph, 2 squared is 4, which is minus 1 mod 5. So it is vertex transitive. So what Boyan and I showed is that this graph has 1 as a simple eigenvalue if and only if one of these following things hold. So we were able to characterize what happens in each of these cases. So if 4 and 5 both do not divide n, or if 4 divides n and k is even, or if 5 divides n and k is not one of these 4 numbers. Okay, so in fact, if you had k equals to 2, you would get an graph isomorphic to if k is minus n minus 2. That's why these things are here. Yeah, so by considering the eigenvalues and some complicated machinery with number theory, we were able to determine this. But perhaps so that this talk would have a second, maybe it's the first proof. I don't remember if I proved anything earlier. Let us look at a very simple case when n is a prime. Then we're going to be able to get much more. So to do that, you don't have to look at complicated roots of unity. You only have to consider some very basic algebraic number theory things. So you can find the eigenvalues, not exactly easily, but other people have found the eigenvalues of P and K. And in particular, the multiplicity of 1 is an eigenvalue. It's the number of solutions for J, such that when I take theta equals this angle here, 2 pi J over n, theta satisfies this equation here. So 2 cos of theta, cos k of theta, k is that number, this is for P and K. K is this k, is equal to cos of theta plus cos of k theta. So in particular, if you would take J is 0, then theta is 0, and then you would have cos of 0, which is 1, and this is also 1. So you would get 2 is equal to 1 plus 1. So J equals 0 is always a solution. So 1 is always an eigenvalue of that Peterson graph, of the generalized Peterson graph, but there could be other solutions. There could be other numbers J such that this also gives thetas that satisfy this equation. Okay, so what do we do in this case? Well, cos of k times theta, it's just tk evaluated at cos theta, where t sub k is a kth Chebyshev polynomial of the first kind. You may not know what they are, but the important thing is that it is a Chebyshev polynomial. It has its own name and its own Wikipedia page, so we can find out the degree of this polynomial. And what we can do is now we can write 2 times cos theta times this polynomial evaluated cos theta is cos theta plus the polynomial evaluated at cos theta. So what does this mean? Well, it means that cos theta is an algebraic number. Like if you move all of this to the right-hand side, you would get that 0 is some polynomial evaluated at cos theta, right? So this thing is an algebraic number from this equation here. So its minimal polynomial, whatever it is, it would divide the polynomial you would get from this business with the TK, with the Chebyshev polynomial. You can know the degree of the Chebyshev polynomial, so some stuff could be done. Sorry. So in other way, without using this equation, we can find theta, we can find its degree as an extension of the rational numbers. And the degree is just the Euler-Toscan function of m prime, where m prime is when you reduce j over n to its lowest form. So the GCD of j prime and m prime is 1, and then its degree will be the Toscan function of m prime over 2. But in any case, we can find the degree in some other way, and this degree has to divide the degree of this polynomial here. Or sorry, the polynomial divides. So this degree is smaller than the degree of this polynomial here. Okay, so just by considering the algebraic degree of cos theta in the 2 ways, you would get that if you have the generalized Peterson graph on a prime number of vertices where p is an odd prime, if its vertex-transitive, then it has 1 as a simple eigenvalue if and only if it is not the Peterson graph. So this statement is cool not only because we didn't really have to work really hard to get it, we only had to consider the algebraic degree of cos theta, but also because it's a theorem of the form blah, 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 blah is true unless the graph is a Peterson graph, which I know that we're all very familiar with and love very much. Yeah, I guess that wasn't a complete proof of this, but the sketch is there. Okay, so other examples of graphs that give possibly cubic graphs, sorry, cubic vertex-transitive graphs where 1 is a simple eigenvalue. You can get it as follows. So you take some graph G that is arc-transitive and it's a multigraph that is cubic. And then you perform this truncation operation where you replace every vertex by a 3 cycle adjacent to the same vertices as before. So you can imagine embedding this on some surface and chopping off all the corners and replacing it with a very small triangle. Because the triangle, it doesn't, you could do higher degree to replace them with other cycles, but you would need to embed it so that you would know which vertex comes next. So we showed that if the graph is connected and cubic and it has a triangle, then it has 1 as a simple eigenvalue if and only if it's one of these things. So if and only if it's obtained from some connected bipartite arc-transitive cubic multigraph using this truncation operation. Okay. So in conclusion, if a graph has simple eigenvalues and you have some other information about it, for example, some information about the automorphism group, then you'd actually know a lot about the graph structure. And there is this inverse relation between the number of simple eigenvalues and the number of automorphisms of the graph. And yeah, so you can prove even more things. If you have graphs with bigger multiplicities, you can look at that star partition and you can look at the vertices that get mapped onto a single eigenspace. So now you have a group of vertices that are going to be matched in that complicated weighted graph from before. They're going to be matched to a specific eigenspace. You can say stuff about the adjacencies of those vertices as well. So you can say stuff about substructures of the graph given these eigenvalue structures. And yeah, so I hope that there's some room for new research. So maybe, Chris, some strongly cospectral operations can occur with simple eigenvalues and star partitions. And I'm gonna end there. That's okay.
Thanks, Krystal.
Thank you.
That was a great talk. I was actually very, I was surprised in the beginning when you said that that most graphs have all simple eigenvalues, because to me that's not intuitive. And then I sort of got the answer to this later because I've mostly worked with vertex-transitive graphs. So yeah.
Yeah, that can be deceptive if you only work with, strongly regular graphs and vertex-transitive graphs. They all have huge multiplicity.
Yeah.
But in fact, almost all graphs are controllable, so it's even a little bit worse.
Yeah, I see. Do we have any questions for Krystal? Okay, so I actually wrote down, I can't remember what my question was, but could you go back to page 11? Okay. I think I had a question there, which you might have answered later in the talk because I don't remember what it was.
Yeah.
Yeah. That was the page 11 before this one.
Oh, yeah. Okay.
Oh, just could you give an idea of the proof of this theorem?
Yeah, so it's going to be exactly like the next one. So what happens here is you have 1 and -1 as eigenvalues. So you have some v and some w, and you can assume both of these are plus or minus 1 vectors. Right? They only have one distinct entry in absolute value, so you may as assume it's plus or minus 1. Okay, so then you formulate like a partition of the vertices into like things that are plus in v and plus in w, vertices that are plus in v and minus in w, and then minus in v and plus in w, and then minus and minus w. Right, so you have this 4-part partition. It partitions the vertices of the graph, and with a small amount of effort, you can show this partition is equitable, and then you can compute the partition matrix, the quotient matrix of this partition. And this it's going to be a 4x4 partition matrix, but whatever the partition matrix of this, the b hat, it has -3 as an eigenvalue. So that's how you show this theorem.
Okay.
So you need to count the adjacencies between these things, but it's possible to do it given the eigenvalue. So yes.
Okay. Okay, thanks.
May I ask a question?
Yes,
Yeah,
Bill.
Hi, Krystal. Nice talk. So
Thanks, Bill.
I wonder if you can say anything about the splitting field of a graph with only simple eigenvalues. So if a graph has only simple eigenvalues, do you expect the characteristic polynomial to have gigantic irreducible factors, or do you expect a lot of small degree irreducibles?
Didn't we say they were controllable?
If the characteristic polynomial is irreducible, which is generally the case.
Yeah.
So
it's huge, right?
Bad.
Yeah. But like those numbers are roots of the characteristic polynomial. So their degree is no more than n.
Yeah.
Right. And they're like totally real. Like all their conjugates are also real. They're also eigenvalues of the graph. So I mean,
never underestimate the difficulty of working with algebraic integers to a degree greater than 4.
Yeah. I mean, degree 2 gives you a lot of problems when you guys are doing perfect state transfer. So I don't really see degree 4 going better for you. So yeah.